Again, I have to plug it in. I need to see what's happening here. Now, when I plug it in, I have 5 times infinity minus 2. Imagine infinity a million. 5 times a million minus 2. What will you say? Where is this quantity going when x approaches infinity? What do you think? 5 times infinity minus 2. What will you say? Don't be afraid to be wrong. It's okay.
The positive answer?
Right, but where is it going? Correct. So 5 times huge minus 2. What would you say? You're correct. It's going to be positive, but what? What will you say?
Positive infinity?
Absolutely. Perfect. The same thing in the denominator. 4 times infinity plus 1. What do you think that is? Anyone?
Positive things.
Say it again.
Positive infinity.
Of course. And this is another indeterminate case. So here it is. We looked at 2 indeterminate cases already. We encountered 0 over 0, which is an indeterminate case, and now we encountered infinity over infinity. This is another indeterminate case. Okay, what do I do now? So I'm going to write it again here. Limit as x approaches infinity from 5x minus 2 over 4x plus 1. Before I show you the technique for this one, I would like to establish something else. Limit as x approaches infinity from 1 over x. The numerator is 1. The denominator is humongous. Huge. Okay, so let's say this. Let's say I have in the function 1 divided by x, and I'm going to plug in numbers towards infinity. I'm going to plug in 40,000. I'm going to plug in a million. I'm going to plug in 20 million. But let's take a look. This says 2.5 and 5 zeros to the left. 0.4025. This one says 0.5 zeros and 1. This one says 0.7 zeros and 5. So what is your conclusion? The limit as x approaches infinity from 1 over x. What is the target? When I divide, let's say a silly example, I have 1 cake and I want to give to everybody on the planet of peace, of 1 cake. When I knock on your door, how much will you get from that cake?
Well, it would be like just a tiny bit, so I guess it approaches 0.
Indeed, absolutely. Every time we divide a tiny number by something humongous, remember what we got? 0.7 zeros and 8. What is this? 0. Excellent. So now we're coming back, so please keep this in mind when x approaches infinity. But if I say limit as x approaches 2 from 1 over x, no, that's not 0. It's 1/2. But when x approaches infinity, 1 over humongous, The target is definitely 0. You're not going to get anything. Nobody's going to get anything. If I have one cake to divide by 7 billion, 9 billion, I don't even remember how many we are right now. Okay, so here's the technique for this situation with infinity over infinity. I am going to factor in the numerator the degree. What do I mean by degree? Well, the degree is 1. So we're going to factor out x. Unrelated to that, I see the denominator also x, because the degree is 1. If I had x squared here and x squared here, I would factor out x squared. And I know you are appalled, and you should be. You should say, what are you doing? X is not a factor in the numerator. X is not a factor in the denominator. You can't do this. Well, here's what I'm going to do. As long as x times these two terms gives me 5x minus 2, I'm okay. And here's how I do it. X times what is 5x? Well, nice, 5. Minus. X times what is 2? Well, 2 over x. So x times 5 is 5x. X times 2 over x is 2. Can anyone help with the denominator? When I factor out x in the denominator, what will I have in parentheses? Because these have to work. This product has to give me 4x plus 1. If it doesn't give 4x plus 1, then it's incorrect. Can anyone give us 4x plus 1? And tell us what we should write in parentheses?
Is it 4 plus 1 over x?
Indeed. And yes, of course, that was the whole point. The whole point was to remove the problem by simplifying factors only. Good. And now, remember what we just established. What will the limit of 2 over x be? Where is this going? Just the limit of 2 over x. Where is this going? Who cares if it's 1 or 2 or 10,000? 10,000 divided by infinity is still 0. So 2 over x, when x approaches infinity, will get closer and closer to what?
0.
Exactly. What about 1 over x? Only when x approaches infinity. 1 over x will get closer and closer to what?
Same thing.
Same thing. Since these are gone, can anyone give us the limit? What do you think the limit is?
It's just 5/4.
That's it. That's it. This is gone. This is gone because they approach 0. Here I simplified. The limit of 5 is 5. The limit of 4 is 4. There is nothing else. I can't change those. So this is another technique, depending on the problem. So what are the techniques we just looked at? Factoring, in the case of 0 over 0. Rationalizing, because it was a radical. The expression had a radical. Still 0 over 0. We rationalized the denominator using this formula. And finally, when we encountered the second indeterminate case, infinity over infinity, we factored out the degree by force. We forced it. X is not a factor here. Theoretically, I'm not allowed to do that. But as long as what I write here matches, I'm fine. So this times this is 5x, this times this is -2, this times 4 is 4, this times this is 1. So therefore the limit, in this case, is 5/4. And it was an indeterminate case. We didn't know anything about it. One concept here that we need to discuss is continuity. What is continuity? So it's better to talk about when a function is not continuous first. A function is not continuous when, number one, it has a jump. We had a jump last time, and I mentioned jump. I'm just going back for a second. I did not recycle these yet. When we graphed a piecewise defined function some time ago, okay, there's a jump. Here's a jump. I'm going to graph one in a minute. A jump. At x equals 0, the function jumps. It's not continuous. So I can draw this piece. I have to raise my pencil or marker of the paper and continue here. So there was a jump. The function is not continuous. When it has a jump, the function is not continuous. That's one option. So jump. So here's a jump. That's a jump. Notice that these 2 points have to be one on top of the other. This is a function because the full point is here and open here. So the function is not continuous when it has a jump. The second possibility, the function is not continuous when it has an asymptote. It has a vertical asymptote. Here it is. Here's the graph of a function that is not continuous because it has a vertical asymptote. This is the vertical asymptote, VA. And there is a third possibility for a function not to be continuous, and that is called removable. Removable. This is removable. And we had a situation last time with that graph that I printed out. If you remember, there was a removable discontinuity. So, a jump discontinuity, vertical asymptote, it's called infinite. Infinite discontinuity. Infinite discontinuity, jump discontinuity, infinite discontinuity, and removable discontinuity. So I'd like to look at a couple of graphs and then move on. So here's my book. Okay, so let's say 47. Is there any discontinuity in 47? Is this function continuous everywhere, or there is a discontinuity?
There's a jump.
There is a jump. Excellent. What about 50? Is this function continuous everywhere, or it has a discontinuity?
It has a whole.
Yes, a whole or removable. Good. What about this one? Is this one continuous everywhere? 51?
No, there's a asymptote.
Yes. In other words, a infinite discontinuity or a vertical asymptote. Perfect. Excellent. Good. So now I would like to discuss one more topic here. It's called continuity at the point. Very important definition. Very important definition. So let's take a look at this graph. Is this a continuous graph? In other words, I'm asking, does it have a jump? Does it have a removable? Does it have an infinite discontinuity? Or is it continuous everywhere?
Looks continuous.
Continuous everywhere. Perfect. Now let's take a look at the point. Anywhere on the graph of this function. Let's say here. For a function to be continuous at this point, the limit from the left, the limit from the right, and the function value at that point all have to exist and be equal. Meaning, the limit as x approaches a from the left, a being, that's the number a, from f of x equals the limit from f of x as x approaches a from the right, and must equal the function value at a. Again, at a, the function is continuous only if these three things happen. The limit from the left exists, the limit from the right exists, the function value exists, and they are all equal. Otherwise, the function is not continuous at that point. Okay, so let's look at a problem and analyze the situation and see if the function is continuous at a particular point. So let's say 63. So f of x is a piecewise defined function, 1/2 x plus 1 for x less than 4, and negative x plus 7 for x greater than or equal to 4. And the question is f of x continuous at x equals 4? That's our question here. Is it continuous at x equals 4? I have no idea. What I am going to do, however, I'm going to write the definition. So the limit as x approaches 4 from the left, limit as x approaches 4 from the right, does that equal to, will these three be the same? All have to exist and all have to be identical. If they're all identical, if they all exist and they're identical, I will say yes. If something happens, then I will say no. Now, the limit as x approaches 4 from the left. 4 from the left with numbers smaller than 4. I have to pick the exact branch, not both, exactly the one that has x approaching 4 from the left. Is it the top or is it the bottom? And you can say, how do I know? You only have to look here, and then you will know. So what do I put inside parentheses here? Do I put 1/2 x plus 1, or do I put negative x plus 7?
1/2 x plus 1.
Correct? Do we all agree?
Yes.
X approaches 4 from the left with numbers smaller than 4. So I have 1/2 x plus 1. I know it's redundant, but I'm going to ask anyway. Are you certain that 4 from the right is in this interval? So then I have to plug in negative x plus 7. what branch do I use for f of 4? I can only use one. Which of these two includes x equals 4? Not both. It will not be a function.
The bottom one.
The bottom one. Why? Because of the equal symbol. So for f of 4, I have to calculate negative 4 plus 7. So for this, I have negative 4 plus 7. That's f of negative 4. Okay, perfect. Now, let's calculate. Can anyone give us this limit? It's a piece of cake because these are polynomial functions. What will you say about the limit as x approaches 4 from the left? So, perfect. So 4 times 1/2 is 2. 2 plus 1 is 3. Very good. So this is 3. Excellent. Can anyone calculate this for us? Again, this is very simple. It's a polynomial function. What do we get? Can anyone plug it in and tell us what we get?
There's still 3.
Very good. Awesome. Can anyone calculate f of 4 for us and tell us what to write? Anyone, please?
3.
Good. What will you conclude? How will you answer this question? Is yes. Yes. The limit from the left equals the limit from the right and equals the function value at 4. Therefore, this function is guaranteed to be continuous at 4. So, conclusion, f of x is continuous at x equals 4. Why? Because I wrote the definition and I checked. The limit from the left gave us 3. The limit from the right gave us 3. The function value at that point gave us 3. So therefore, the conclusion is they all exist. They're all equal. Therefore, the function is continuous at x equals 3. At x